Thank you. Thank you for the kind introduction. So let me get started. The first question is, why do we want to have privacy on Stellar? Stellar is a wonderful technology, hope you all agree by now. It is decentralized, permissionless. It offers instant settlement within just a fraction of a cent. And it's getting better with all the performance updates and all the features, and which makes it very good for traditional payment use cases. However, just like any public blockchain, Stellar is globally visible, which means all the states, all the history, all the transaction details, all the individual identities are visible. And even though the individuals that transact are identified pseudonymously, it doesn't mean anything in privacy because these addresses' identity can be leaked. And to build financial applications for mass adoption, there's also this regulatory considerations. On one side of the spectrum, you have the data protection laws that needs to protect user confidential financial data. And on the other hand, there is the illicit finance requirement, which needs to provide certain transparency when needed. And great financial products need to consider both. But I would argue that currently, most blockchains as is not doing good on either. So as a result, Stellar blockchain faces an adoption ceiling, especially within institutional players without privacy features. So the next question is, what type of privacy features are we looking at? So in terms of what can be protected, there is the account states, the transaction details, and the identities. And depending on the application, it needs to protect some variant or some subset or all of them. And selective disclosure is a key function because of regulatory needs and auditing needs. And it's a two-way street. In one direction, the account owner should be able to choose when I need to prove certain ownership or certain state. And on the other hand, the auditor at an unannounced timing should be able to view certain aspect of some transactions for compliance. There's no one-size-fits-all solution here. Broadly speaking, there are three types of approaches out there, depending on privacy features, cryptography features, the broad spectrum. But these are the three broad approaches: privacy pools, ZKVM, and if you're interested, make sure to stay around for the next two talks by Nick, Lucian, and Matthew. They'll be great. What I'm going to talk about today is confidential transfer, which is the work we have been doing internally at Stellar. This work is also similar to other work has been done by other blockchains, so we're not the first. So why confidential transfer? In my opinion, the best advantage of confidential transfer is its simplicity and familiarity. It is just like a normal P2P payment where the identities still remain transparent, but there's confidentiality built on top of it to make certain aspects, like the transfer amount, account balances, secret. It is simple in terms of cryptography, and it is efficient for computation. I'm not a cryptographer myself, but I know just enough cryptography to tell you how sexy that word simple is. And for auditing, because of a regulatory, they have certain background. For the regulatory story, it is much easier if the model is simple and familiar. That's why I feel like confidential transfer has a very clear, strong regulatory story in terms of existing KYC, KYB, and with additional compliance features built on top. So the goal here is that we want to build a prototype that balances, combines usefulness and compliance so that others can adopt it and build upon. To take a quote from Danielle yesterday, we build right so others can build upon. Now, let me walk you through the journey of building confidential transfer through the eyes of a token. What is a token? I'm sure most of you are familiar already. Token is just identifier of value. It's a symbol, but what makes a token meaningful is the underlying value. And the accounts are just identities of these value holders in the traditional or classic stellar blockchain is just a public key for authorization. And the account balance is just a numerical value that identifies the quantity of the holder. And the token contract is just a bookkeeper. So in a standard token, you have an issuer, you have identities like Alice, Bob, and Carol, and there's a bookkeeping ledger that keeps track of the amount and states. So when the transfer happens, usually Bob submits a transfer operation that has a sender and the receiver, and then the transfer amount. So all of this is public and transparent on the blockchain. For a confidential transfer, the model is very similar. You still have Bob and Alice, and Bob submits a transfer operation with source and destination included. However, instead of sending 30 as a clear text, it encrypts it and sends the encrypted value on chain. And this encrypted value is only meaningful to Alice, Bob, or whoever has a key to view it, but it's meaningless in terms of everyone else. So what appears like on the ledger is just some random string of hash. What's important to note here is that even though no one can make sense of the value, what they can do is to verify the correctness via some magical cryptography properties, which I'll introduce in a bit. So how does it work? Now the account has an extension. In addition to the public key, there's also an encryption key. And the balance has an extension called confidential balance. And the encryption key, the account has a key pair where the account will store the decryption key, just like its secret key, in a wallet. This decryption key can decode the confidential balance into plain text. And these confidential balances can be added and subtracted via homomorphism. So now here's just a picture. Alice has a standard balance and now has a confidential balance initiated at 0. So a brief introduction of homomorphic encryption. It basically states that if you encrypt two values, add them up, it is equivalent of if you add those two values and encrypt it. In other words, it allows linear operations such as balance update directly over the ciphertext without revealing the underlying plaintext. And one cool feature of linear homomorphic encryption is that it enables very simple cryptography primitives such as the sigma proof. Sigma proof is part of zero knowledge proof, which is a backbone of securing the logic of the contract. So zero knowledge proof is used here to enforce some internal logic and properties of the contract, such as conservation of value and then equality of different encrypted values. So for the confidential token, there's two new operations for deposit and withdrawal, which moves the balance between the transparent and confidential account. So for the deposit, it looks very similar as what a normal deposit looks like, but the amount is an encrypted value of the transfer amount, in this case 30, encrypted with Alice's key, and the withdrawal goes the other way. One thing to mention that the withdrawal requires a proof. Like I mentioned earlier, the zero knowledge proof is the backbone of securing this contract logic. So in this case, zero knowledge proof is required to ensure that Alice has the right balance to make the withdrawal. Now, let's talk about transfer. So because now there's two account balances, Alice and Bob can transfer to each other confidentially. And this is sort of what the transfer blob looks like. Has a source destination, and the transfer amount now is encrypted multiple times. One for Alice, one for Bob, and one for auditor, whoever needs to look into the transaction and the proof. So the zero knowledge proof is required here to ensure that these three transfer amounts are indeed transferring the same value, and the transfer amount needs to be non-negative, and Alice has the correct balance. Okay, so that was pretty easy. It's very familiar, simple mental model. But I'm just going to introduce you one caveat or one challenge that makes this picture a little bit more complex. So in order to generate the withdrawal, Alice needs to attest to her balance, which means that she needs to lock in the current balance. But if Bob, an innocent guy Bob, is just sending her money, then it keeps changing her balance, which means that she cannot withdraw her money. This innocent feature can turn into a denial of service if used maliciously. So the solution is simple. Just to split out the balance into two parts. There's available balance, which Alice can withdraw from or send to someone else. But there's a pending balance, which any incoming transfer will have to go through first. And because of this separation, in addition, there's a new operation called rollover that needs to make this pending balance available. Okay, so now we have everything we need for the demo. So let me do that. So what you see here, two terminals. I respect the hell out of you if you are a UX developer. I am not, so I'm going to just show you in very raw form, core engineers' favorite UX tool. So here you have it, two terminals. On the right-hand side, you're going to see what mimics the blockchain. So anything you interact with the blockchain, you submit transaction, you look at the event, you look at the state, you can see it here. But on the left-hand side is your off-chain client, usually your wallet, and the stuff that no one else can see but you. Oh. Okay, so let's start the demo. A confidential token is just a standard token, so it needs to register users. So in this case, I'm just going to make up a name, a confidential demo token, CDT, decimals is fine. So it's going to create a token. This point is still a standard token, nothing special. And it's going to register Alice and Bob as two authorized users of the standard token. So the next step I'm going to do is to generate these keys for confidential, the confidential extension. This way they can decrypt the transaction. So there's nothing in here yet, so I'm going to copy paste this command over here. So the key has been generated. And the key is, if you just look at it, it's just like a random 32-byte string. It's a group element. So what's going to do is to next is to load these three keys, and then this token is going to register its confidential extension and approve Alice Bob as the confidential token user, and add this auditor key as the auditor for this entire token operation. So that's done. I'm going to next. So next, in order to make a transfer, there has to be some setup. First, the issuer has to mint some token into the account of Alice and Bob. So let's do that, 1,500. And now you see a state diagram which has the state of what the public ledger, what everyone can see. The transparent balance now is 500 and 1,000 from Bob and Alice. The available pending balances are all 0 at this point. In order to make this usable, Alice needs to first make a rollover operation to make, not yet. Alice needs to first deposit some amount into her balance, obviously. So it's going to do that, and so is Bob. So now you can see the pending balance is non-zero. And then we know it because we just saw it, but this one is a 500, this one is 250. So the next operation is the rollover. Alice needs to make this pending into available in order to send the amount to Bob. So let's just do that. Okay, so we did it, and then there's a proof needed for the rollover to happen. But honestly, this proof is pretty boring, so we're not going to look at it yet. We'll look at something more interesting later. So I'm just going to provide the proof. Just trust me, this proof is correct. Or don't trust me, the chain should know it. So the chain just approved it. So Alice made the rollover. Now the pending balance is 0. Available balance is something. And we know this something is 500. That's what she started with. So now we are ready to make a confidential transfer. Okay, so this is the most interesting part. I'm going to pause and explain it a bit. So in order to do the transfer, because this amount is from confidential to confidential, so you don't submit this amount on chain anymore. So all you do with the transfer amount is to generate the proof that you have indeed transferred the amount and that the contract state between and after is consistent. So let's say Alice transfers amount 123. This is all happening in my wallet, by the way. And then provide the Alice's key, Bob's key, auditor's key. They will all get the encrypted value of this amount 123. And then Alice also has to attest to her current balance because she needs to create a proof for that. Let's just do that. Okay, so the proof is created. Let's just look at it. It's a big blob of text, but what it contains is a sigma proof that I mentioned earlier. In addition, it has a ZK range proof of the transfer amount, ZK range proof of the new balance, and the encrypted amount of Alice after the transfer, the encrypted transaction amount in Alice, Bob, and the auditor's keys. So now let's look at this transaction amount. You know what I typed in earlier, 123. So how would Bob know? He is not involved in this transaction yet, right? He doesn't know what amount he's getting. So let's try decrypt with Bob's key. So the decryption function in Bob's own wallet, if they take out this text and run it in his own wallet, he will get amount 123, which is consistent with Alice's. And what about the auditor? So far, we haven't really touched the auditor at all. The auditor doesn't maybe not even exist on the chain. It's just a key that has to be registered. So, auditor. So auditor gets the same amount. So let's just provide the proof, and we will see the transaction. So the chain will validate this proof and then make the transfer. So now this text is different. Bob and Alice can decode their right. So this is exactly what you see on the right-hand side, but I'm just making it more expanded. So Bob now has a different transfer, different balance, which we can decrypt again with Bob's key, 323, which matches 250 plus 123. So everything is correct, and we know everything is correct because the zero-knowledge proof enforces that. So if I don't have time to show you, but if Alice, say, cheated and modified the proof, or if someone else used the key, try to decrypt any of these amounts, it will not work. If you're interested, grab me afterwards. Happy to show you. So that's it for the demo. Some stuff under the hood we're going to skip, and then the transfer proof states some statements. We already went through some of it, so we're going to skip. I want to spend the last minute I have on the future opportunity. So I think in terms of the contract functionality, it is pretty much simple and complete. I would say in terms of auditor, there's a global auditor that can look through the entire transaction to make sure everything is correct. But the auditor has to do so in a very inefficient way. It has to boil the ocean by decrypting every transaction and reconstruct the transaction graph. So can we do something better? So this is an open question. We need to work with everyone to find a standard for. So how do we do this auditing better? Can we maybe do auditing in a more scoped way so that different auditors have different jurisdictions or different responsibilities? And then maybe more safety in auditing, including like key rotation, key expiry. Or can we build a smart contract in a way that allows auditing to be easier, such as proving my account balance never exceeded a certain amount, within certain time period. I think that's much easier to do on the contract side if we provide the right type of data structure. So the next step, we are going to do a more formal specification and security proof of the method. We're going to do Stellar Core and Soroban support. And we want to work with you guys to define the confidential transfer standards and all these higher level solutions like the client that I demoed, the compliance tools, still needs to be built. So we need to have everyone's input and work with the ecosystem. And the project repo, and then there's a discussion thread going on. Feel free to check them out. The repo will contain the code eventually, but it's the PI is still in process, so wait a bit. But we would love to hear from you. Thank you very much.